Welcome back. This is Chapter 2, and in this section we will work through a complete example on earthwork measurement. In the previous part of this chapter, we learned about site excavation, bulk excavation, deep excavation, working space, depth classification, and the units of measurement used in quantity surveying. Now, we will apply those concepts step by step using an actual project example. Worked example, earthworks for a single building, detailed. Given, project data. Building plan, 20 meter by 10.0 meter. Trench nominal width 0.60 meter. Trench depth 1.80 meter. Working space each side of trench 0.6 meter. Bulk excavation to whole building area to depth 1.20 meter. Topsoil or site clearance depth equals 0.15 meter typical. Assume 20 cubic meters of surplus spoil will be carted away. Assume excavated soil is suitable for reuse for backfilling. If unsuitable, we would import borrow. Bulking factor 1.25. Compaction factor 0.90. Step 1. Building footprint and perimeter. First, we calculate the building's plan area. 20 times 10 gives 200 square meters. Next, the perimeter of the building, which will define the strip footing trench length. 2 times the sum of 20 and 10 gives 60 meters. This perimeter will be used repeatedly when calculating trench excavation, concrete, and blinding. Step 2. Site clearance, topsoil removal. We remove the topsoil because organic material is unsuitable for supporting structures. Topsoil depth is 0.15 meters. So the volume of site excavation is 200 square meters times 0.15, giving 30 cubic meters of topsoil. This material is not used in structural backfill, so later we will subtract it from the usable spoil. Step 3. Bulk excavation, B. The entire building footprint must be lowered by 1.2 meters. So the bulk excavation is 200 square meters times 1.2 meters, which equals 240 cubic meters, measured in bank volume. This forms our reduced level, that is, the level where the foundation trenches begin. Step 4. Trench excavation, DE. The nominal trench width is 0.6 meters, but we need working space of 0.6 meters on each side. So the top width of excavation is 0.6 plus 0.6 plus 0.6 is equal to 1.8 meters. We excavate the trench down to 1.8 meters depth. So the full excavation volume is perimeter 60 meters times 1.8 top width times 1.8 depth equals 194.4 cubic meters in bank condition. But remember, the bulk excavation already removed the first 1.2 meters across the entire building. So we subtract the overlapping volume. 60 times 1.8 times 1.2 is equal to 129.6 cubic meters. The remaining deep excavation beyond the bulk level is 194.4 minus 129.6 is equal to 64.8 cubic meters. This value, 64.8 cubic meters, is our deep excavation, DE. Step 5. Total excavation volume, southeast plus B plus DE. To get the total in situ material removed. Topsoil, 30. Bulk excavation, 240. Deep excavation, 64.8. Add them up. 334.8 cubic meters bank volume. Step 6. Concrete volumes in trench. Part of the trench will be permanently filled with concrete. We assume the footing width is 0.6 meters and the thickness is 0.5 meters. So the footing concrete volume is 60 times 0.6 times 0.5 is equal to 18 cubic meters. We also place a blinding layer of 50 millimeters. 60 times 0.6 times 0.05 is equal to 1.8 cubic meters. So the total concrete filling the trench is 18 plus 1.8 is equal to 19.8 cubic meters. This must be deducted from the trench when calculating backfill. Step 7. Backfill requirement. We now determine how much soil must be returned to the trench after the concrete is poured. The full trench excavation was 194.4 cubic meters. Concrete occupies 19.8 cubic meters of that. So the backfill needed is 194.4 minus 19.8 is equal to 174.6 cubic meters in bank volume. Step 8. Spoil available for backfill. Not all excavated soil is usable. We must exclude topsoil, 30 cubic meters. Concrete occupying space, 19.8 cubic meters. Cart away, 20 cubic meters. So from our total excavation of 334.8 cubic meters, the net usable spoil is 334.8 minus 30 minus 19.8 minus 20 is equal to 265 cubic meters bank. This represents the amount of suitable material available on site. Step 9. Compare backfill required versus available. Backfill required is 174.6 cubic meters. Available soil is 265 cubic meters. We have a surplus of 265 minus 174.6 is equal to 90.4 cubic meters. Therefore, no imported borrow fill is needed. Step 10. Bulking and compaction, practical. In practice, soil changes volume when moved. Bulking factor is 1.25, meaning soil expands 25% when excavated. Compaction factor is 0.90, soil reduces to 90% of loose volume when compacted. Loose volume available is equal to 265 times 1.25 equals 331.25 cubic meters. Loose volume needed for backfill equals 174.6 divided by 0.90 is equal to 194 cubic meters. Loose surplus equals 331.25 minus 194 is equal to 137.25 cubic meters. Converted back to bank, this is roughly 110 cubic meters surplus. This confirms again that no borrow fill is required. Step 11. Cart away, example. If the client wants no surplus on site and you need exactly to balance cut and fill, you would cart away the surplus bank volume, approximate 90.4 cubic meters bank. In practice you might cart away the initial assumed 20 cubic meters, plus an additional 70.4 m superscript 3 if you wish to have zero surplus. Alternatively, reuse extra spoil for landscaping or temporary bunds. Always check local disposal costs and environmental restrictions. Final summary. In summary, total excavation, 334.8 cubic meters. Concrete in trench, 19.8 cubic meters. Backfill required, 174.6 cubic meters. Reusable spoil available, 265 cubic meters. Surplus, about 90 cubic meters bank. This example demonstrates how quantity surveyors calculate excavation, avoid double counting, determine backfill needs, apply bulking and compaction factors, and evaluate whether borrow fill or cart away is necessary. Thank you for watching. In the next lesson, we will prepare a complete takeoff sheet for this example and show how to present it professionally in a bill of quantities.